This video will provide an example of overfitting in feature selection. By the end of this video, you should understand why overfitting is a problem in predictive models and how you can prevent overfitting in predictive models. The R code used in this video is available on the learning management system. It uses the data files dcelectricity_train.rds and dcelectricity_test.rds. You should download those files now if you'd like to follow along. Following from examples in previous videos, suppose we're interested in modeling the relationship between the high temperature and electricity demand. We saw in previous videos that the relationship is nonlinear, and adding polynomial terms improved predictions from the model. But that leads to a question: how many polynomial terms should we add? This is a feature selection problem. You're trying to decide which and how many features to include in a model. How might you make that decision? We want models to make the best predictions possible. And what this means is a low value of the loss function because it embodies our preferences over prediction errors. So what you could do is train many models, including many different features, in this case, many different orders of polynomials of high temperature, and then choose the model with the lowest value of the loss function. We're going to go through and train several different models with different orders of polynomial for the relationship between electricity demand and high temperature. To do this, I'm going to load the dcelectricity_train.rds data file. In the code that I have here, I'm going to train 7 different models with polynomial terms of high temperature to the first degree, the second, third, and so on. And then after that, I'll evaluate each of the models on my electricity data using the root mean square error loss function. Let's run all of those models now. Looking in the output window, you can see the root mean square error of each of these models. With just the high temperature to the first power, the root mean square error is 281,267. Adding a squared term takes it down to 219,145. Adding a cubed term takes it down to 219,042. And so on, all the way down to adding the 7th power term takes it down to 217,767.6. You can see in every case, as we've added a polynomial term, the root mean square error of the model decreases. This is something you should expect. Remember, as we add features or additional flexibility to our models, that gives them an additional way to remove error from the model. A model is always going to minimize the value of the loss function, given the flexibility that you provide it. So adding these additional features will always reduce the value of the loss function. Going back to my code, we had the lowest value of the loss function, including 7 polynomial terms. I'd like to create a visualization of the predictions from that model to see how well they fit. So first I'll use the add predictions verb to add the predictions from model 7 to my electricity data table, and then I'll create a visualization showing the original data using black dots and the prediction for my model using orange dots. Looking at the visualization, you can see the predicted values from the model do a relatively good job of following the pattern of the relationship between electricity demand and high temperature. I'm curious though, how this model would do predicting electricity demand in the future. So going back to my code, I have a second data file, dcelectricity_test.rds. I'll load that and save it in the elect2 file. I also glimpse both the original data and this new data file to see if they have the same information. Looking in the output window, you can see both elect and elect2 have the date, high temperature, low temperature, and demand variables. Remember, we added predictions from model 7 to the original elect tibble. Those are not in the elect2 tibble. You'll also notice that the dates in these two files are different. The elect tibble contains April 1st, April 2nd, and so on in 2016. The elect2 tibble contains January 1st, January 2nd, and so on in 2016. Because I constructed these two data files, I can tell you that the original elect tibble contains data from April, May, June, July, August, and September, and the elect2 tibble contains data from January, February, March, November, and December. So let's take a look at how well that model with 7 polynomial terms predicts electricity demand in this new data set. How can we do that? Well, going back to my code, I can use the RMSE function from the Model R library. First, I'll run it on the elect tibble so we can remember what the model fit was on that tibble, and then I'll evaluate that same model's predictions on the elect2 tibble. Looking at my output, if you remember, the root mean square error from the original model was 217,767. On the elect2 tibble though, the root mean square error is much larger. It's 1,312,400. This is a huge difference in prediction error. So let's take a look at what happened. Going back to my code, here I'm going to create predictions from that same model on the elect2 tibble, and then visualize it the exact same way I did before, showing the original data as black dots and the predictions from my model in orange. I'll run all of that code. Let's take a look at that visualization. You can see this is very different. The model predictions are very inaccurate when the temperature is really low. In fact, they're predicting levels of electricity demand that are well below zero. What's happened here? Because we decided to evaluate the model using the root mean square error on the same data that we trained the model on, we overfit the model and decided to include too many polynomial terms of the high temperature. When you take an overfit model to new data, it can generate wildly inaccurate predictions. And that's what we see here. So what could we do instead? We could evaluate each possible model, not using the data that we trained it on, but out of sample fit instead. So going back to my code, what I do here is I take each of those models that we trained on the original data and compute the root mean square error from that model on the new data. I'll run that code. Looking at the output, you can see the root mean square error when there's just a single term of high temperature is 677,054. It drops substantially adding a square term. It drops even more adding a cube term. But then after that, the root mean square error starts to increase. This should suggest to us that maybe including a third polynomial term is probably as far as we want to go if we want an accurate model. What we saw here was an example of overfitting. This is the principal challenge you're going to face with feature selection. You can always improve the predictions of your model on your training data by adding additional features to your model. This can cause you to add irrelevant features. In the case that we saw here, that was too many polynomial terms of the high temperature. This can reduce the accuracy of your model when predicting out of sample and lead to models that have wildly inaccurate predictions out of sample. Out-of-sample evaluation can help you determine which features to include. When you add additional features to a model, it doesn't always improve the value of the loss function when you compute that loss on out-of-sample data. Evaluating out-of-sample also simulates the process of acquiring new data and testing your model predictions on that new data. Out-of-sample evaluation is a standard practice to reduce the tendency towards overfitting. Be aware it's not a cure-all. You can still overfit models if you use out-of-sample evaluation, but it goes a long way to reducing the risk.